We've just learned about a Chinese breakthrough that could completely change the game for stealth drones, a technology that lets them stay aloft 3 times longer while using half the energy. In this video, we'll unpack how this is possible, why it matters strategically, and what it means for the future of military aerospace. We'll journey through how the system works, the advantages it gives China, and how it shakes up the balance of power, so stay tuned. Because this isn't just another tech upgrade, it might be the next leap in aerial dominance. Dual synthetic jet, or DSJ, it is a flight control method that uses air movement rather than large mechanical parts to steer and stabilize an aircraft. Instead of relying on control surfaces such as flaps or tail fins, DSJ integrates small modules within the wings or body that generate precise bursts of air. These bursts are created by ceramic plates vibrating inside chambers, forcing air in and out in quick, controlled pulses. The dual aspect arises from having two chambers that work alternately. While one chamber pushes out air, the other resets, ready to produce the next pulse. This alternating action distributes mechanical stress and significantly extends the system's lifespan. In earlier single-chamber designs, frequent vibration caused faster wear, but the dual configuration reduces that issue. By removing mechanical control surfaces, the drone's shape becomes smoother and more aerodynamically efficient. Fewer protrusions also mean less drag, which directly improves energy efficiency. In controlled tests, this design has shown the ability to reduce energy consumption by approximately half compared to conventional systems. Another key feature is responsiveness. The air pulse system reacts in milliseconds, allowing the aircraft to make subtle adjustments without physically moving large surfaces. This provides a more stable flight, even in challenging wind conditions. Because the DSJ system is built into the airframe, there are fewer exposed moving parts to maintain, reducing both maintenance time and cost. There's also an intriguing potential for DSJ to function in varied environments. The enclosed design can handle sudden changes in air pressure better than mechanical controls. This could allow DSJ-equipped aerial vehicles to operate from unconventional starting points or transition between different atmospheric layers more smoothly. Overall, DSJ offers a combination of efficiency, reduced wear, and aerodynamic advantages. The result is an aerial platform that can fly for longer periods, require less energy, and maintain better long-term reliability, all without relying on heavy, complex mechanical systems. This makes it a notable innovation in the evolution of next-generation aerial technology. The introduction of DSJ technology creates several clear advantages in the design and operation of aerial vehicles. Extended operating time. The most striking benefit is flight duration. Reducing energy consumption by about 50% allows batteries or fuel supplies to last significantly longer. When combined with efficient aerodynamics, this extends continuous flight time to as much as 3 times longer than comparable designs. For applications like environmental monitoring, mapping, or long-distance surveying, this can be a game-changer. Lower energy demands. DSJ's ability to operate with half the energy means more flexibility in power source choices. Electric aerial vehicles can use smaller batteries without losing range, while fuel-powered systems can carry less fuel, reducing weight and further improving efficiency. In turn, this can lower operational costs and environmental impact. Aerodynamic efficiency. Without traditional fins and flaps, the airframe can be designed with smoother contours. Reduced drag means higher cruising efficiency, more stable gliding, and better performance in varying wind patterns. This opens possibilities for sleeker, more compact aerial designs. Durability and maintenance. The dual-chamber structure reduces stress on each component. Since there are fewer large moving parts exposed to the elements, the design is more resistant to wear from weather conditions, turbulence, or temperature changes. Over time, this could translate into lower maintenance requirements and longer service intervals. The DSJ modules are compact and can be positioned in different parts of the airframe. This gives engineers greater flexibility when designing specialized aerial vehicles. The technology can be adapted to both fixed-wing and blended-wing body layouts, as well as unconventional shapes intended for specific tasks. Potential for multi-environment use. Because the DSJ system is sealed and resilient against pressure fluctuations, it may be possible to launch these aerial vehicles from less traditional environments. This versatility can open up new approaches to deployment and broaden the types of missions or tasks the aircraft can handle. In short, DSJ isn't just about efficiency, it's about enabling a wider range of applications while keeping costs and energy demands low. The combination of endurance, adaptability, and reduced maintenance requirements makes it a forward-looking development for future aerial projects across multiple industries. The emergence of DSJ technology could influence aerial design well beyond its original research environment. Impact on design standards. Aircraft designers may begin rethinking how they approach flight control entirely. By removing the need for large moving parts, DSJ could encourage more aerodynamic, energy-efficient airframes in both small-scale and large-scale projects. This has the potential to become a standard feature in future unmanned and possibly even manned aircraft. Boost for sustainable aviation. Energy efficiency is increasingly important in aviation. Cutting energy use by half supports global efforts to reduce emissions and operational footprints. For industries focused on sustainability, DSJ provides a path toward aerial vehicles that can do more with less energy, aligning with environmental goals. Applications in long-duration operations, whether used for research, mapping, communication relays, or infrastructure inspection. DSJ-equipped aerial vehicles can stay airborne for extended periods without requiring frequent landings. This could improve efficiency in industries like agriculture, where continuous observation over large fields is valuable, or in telecommunications, where aerial platforms can serve as temporary high-altitude network nodes. Encouraging innovation across sectors. When a breakthrough occurs in one area of aerospace engineering, it often inspires advancements elsewhere. DSJ principles could be adapted to new types of air mobility platforms, hybrid aerial terrestrial vehicles, or even atmospheric research craft capable of operating at high altitudes for days at a time. Market and industry adoption. If DSJ proves reliable in long-term operation, it could attract significant investment from commercial and scientific organizations. Manufacturers that adopt the technology early could gain a competitive advantage, especially in markets where efficiency, endurance, and low maintenance are top priorities. Potential for global collaboration. Rather than being confined to one nation or region, DSJ technology could be developed collaboratively between research institutions, aerospace companies, and environmental organizations worldwide. By sharing design improvements and operational data, the technology could advance faster and be applied in more diverse ways. In essence, DSJ technology represents more than just a control system upgrade. It signals a possible shift in how aerial vehicles are designed and deployed. If widely adopted, it could lead to a new generation of aircraft that combine efficiency, adaptability, and sustainability in ways not previously possible. To dive deeper, don't forget to like, share, and subscribe. Thank you for watching Space Race.